Test. test. I will start my lecture at 10:30. So in the meantime, yeah, you can try to do this question. Yeah, I understand today you all have the test letter. I will try to finish it by 11:15 today. If cannot finish the material, then well, we still have Wednesday. Yeah, this week I will just cover. I will finish this analysis of algorithm and introduce another one is the some application of using the stack and queue. So yeah, then yeah, using the transform and conquer technique in maybe Wednesday. That one should be just a small application. Yeah, because that one related to later if you learn about the compiler technique. Yeah, how compiler actually work behind. Yeah, you need to have the knowledge how this kind algebra expression. Yeah, they're able to do the how the computer actually compile a string, a given string, and then sort out the order, the compilation order, all this. Yeah, so that one will cover in the Wednesday lecture. So these are the things we will cover this week. Then next week will be cover about the searching. So then the assignment wise, assignment 1, 2, 3, 5. Assignment 5 will be released. Actually, I can release any times. Yeah, just I'm maybe close to Wednesday. Since you today you got test, maybe after your test, yeah, for the assignment. So assignment will be average will be about 2 weeks times for you to try it out. Yeah, too bad. Every day got test. Yeah. I would say that the lecture wise, I try not to because those material. To be frank, all the material, the key concept theory is already in the notes. So yeah, if you're comfortable to read through the notes, you can understand the things. Actually, it's fine. So lecture wise, mainly I would like to let you all to asking question. That's why YouTube is no choice because the class size is 600. If the class size is too small, that like now only 38, 36, 38 student attend, maybe lesser, then maybe using Zoom is easier. Yeah, I trying to let you have more chance to ask some question. I observed that during the last lab test, yeah, many people just last minute start reading the code. Yeah, you find that actually it won't work one because you read through the code, you just we won't ask the if you can expect that the lab test too, I would ask the same question again. So yeah, mentally prepare. No point to memorize the code, particular question, particular type of question. Yeah, then you will end up if it didn't turn out, then in your mind all are about that particular solution. You cannot think out another solution. Yeah, to solve the actual question. Yeah, that is very sad sometimes. Yeah, in fact, yeah, so far I observed the viewer, the number of view in the past two lecture probably less than 500. That means still a lot of students didn't watch it. Yeah. Well, it's okay because the notes actually already cover. I already tried to put all the technical, the key concept inside what I want to set. Mainly is inside the notes already. So basically, you read through the notes. Yeah, the information the knowledge you need to know is there, And this module, you find that 80% CA is about the coding, the programming. And well, this part, especially these two lecture, is mainly there's a final quiz, another 20%. Yeah, that is the concept part. We will test you. That's the only 20%. So I would say that the lab is still assignment is still quite critical. Yeah, you need to practice to ensure that you're able to implement, to realize the algorithm. I think this is what one of the key learning outcome we want to deliver in this module. Yeah. So what does X represent? So X here is just can be any number, and you can see that it won't affect the result here. Yeah. What does X represent in the function of power 2? It just give you a number. It's a X power to, yeah, basically you're trying to calculate X power to something. X power to n. Yeah, so I think this is a part. Yeah, I think last week let me start the lecture today, 10:30 already. So in the before the recess week, you have learned about how to analyze the time complexity, and then in the learning you realize that time complexity or complexity, you are trying to time complexity, you're trying to count the number of primitive operation. So in fact that like this kind of question, you don't really have to know what exactly they are trying to calculate. Yeah, you mainly focus on find out what is the time complexity, the complexity of this particular algorithm. Yeah. The what exactly this algorithm trying to do is not so critical in this question. Okay, then in the before recess week, you have learned about the time complexity. You need to basically the key is like a lot of time is trying to count the number of iteration, or recursive call, because all this affect the computational time a lot more than just one operation, how much time it take. Because all the operation, assignment, declaration, or any arithmetic logic operation, the time they take is very small. It's just a constant time. Yeah. The key is you repeatedly keep running the particular operation many times. The computational times will increase. That is the time complexity we concern about. So that is one thing. Another thing is when there's a if-else statement, or there's some switch case, or maybe there's I think we also show you, and there's a while loop. They may stop in the halfway. In certain circumstances may stop early. In certain system may stop later. So all these will causing that under different scenario you have different time complexity. And then so in the analysis we need to consider best case, worst case, and is average case. Yeah. So this is what we need to do when we analyze the algorithm. And then analyze all this. One of the so far the hardest one may be something question like this. You need to find the recurrent equation. Yeah, you can see that here in this question. Where's my cursor? Here. So in this question, I have done the recursive call here. Yeah. So you need to figure out what is the here the question is ask you to find the recurrent equation of the given for the number of multiplication. So here I only concern of what is the number of multiplication. So you just need to focus on multiplication operation. Yeah, this is quite common we do in the test or something like that. Yeah, or in practice. Yeah, because we can't analyze everything. Yeah, so we just pick one of the operation, trying to calculate. Yeah, trying to find out the number of this particular multiplication operation. Yeah, so here you can see how many. So first you need to find out. Okay, then here I make the question a little bit easier so that you can finish it in few minutes, I guess. Yeah, it's a power. So the n is power of 2. Yeah, so it's n is equal to. So implied that for sure this n is an even number. Right? All the power of 2 definitely is an even number. 2 or 4 or 8 or 16, 32, 64, 128, 256. All are even number. So even number. So if even number, I definitely execute this part. So of course, in practice, you need to consider best case, worst case. But here, since I already make the assumption, so this line you don't need to consider. It won't happen in this scenario when the n is an even number. So implied that you will do 1 multiplication, 2 multiplication. So in each recursive call, you will do 2. You will find that you will do 2 multiplication. So in each recursive call, I will do 2 multiplication. And then I recursive call the n by half. So the n will reduce by half in the next recursive call. Right? Yeah, so this is the recurrent equation. Of course, trying to solve this recurrent equation, okay, I already tell you that the n is equal to power of 2. So, and also we know that when my n equal to 1, yeah, here, n equal to 1, yeah, there's no multiplication. So the base case, no multiplication. In each recursive call, you will do, after you return, you need to do 2 multiplication. 1 is here, 1 is here. Yeah. So then then every recursive call you read, yeah, okay, here I call t, forgot. T, then n over 2. So when your n is equal to by half already, so this one you expect you will also inside that recursive function, recursive call, you will repeat 1 more times. So if you have another 2, then you will further reduce by half in another recursive call. So you keep doing this. That means every recursive call you will do 2 multiplication. And then come with 2 multiplication, then divide by, the sides will reduce by half, by half, by half, by half, by half. Eventually, your n will equal to 1 in one of the call. Yeah, so you keep doing it. So you will reach certain, yeah, when you keep doing this k times, yeah, k times, then here implied that you need to do 2 k times. Yeah. Then the question is like, when is the k? How many recursive call you need to do? Yeah. So that means this one is when n over 2 power to k. Every time by half, you do it k times. I need to know what is the k. So when is the last one? When this thing equal to 1, right? So implied that, yeah, when is n equal to 2k lah. Yeah, this is actually at the beginning already give you. So what is k? I think someone already give the answer. Yeah, log 2n. So implied that how many 2 are there? 2 plus 2 plus 2 plus 2. So total, you expect that you have 2k. You have log 2n, 2 multiplication operation. in total. This is the total number of multiplication operation you need to execute in this whole call, this whole function call. Yeah, every recursive call you will have 2 multiplication. So this is the total number. So implied that is the total number is 2 log 2n. Yeah. So this is how we count the number of primitive operation. Yeah, when you have encountered the recursive function, you need to write now the recurrent equation, and then normally there's a base case. Yeah, the base case can be 0, can be 1, can be anything. Yeah, but definitely that is the last case you reach. Then there's no more recursive call. You expect that the recursive function will keep every time a recursive call, then the problem size should be reduced in certain form. Yeah, it can be linearly decreased, can be geometrically decreased. Yeah, depend, whatever. You can in any form. The problems, but the problem size, you expect that it should be reduced over the times. Yeah, if you keep increasing or remain unchanged, then your recursive function will not stop forever. Yeah, so as I said, algorithm, definitely you will terminate in the finite times. So you expect that the problem size normally will reduce in certain form. Yeah, so the thing is like in different form, they will give you different time complexity. The number of primitive operation will be different. Depend how you reduce. Depend how your recursive call, and depend how you reduce your problem size in every recursive call. Yeah, so that all will affect the time complexity. Yeah. Well, I think there are another 2 or 3 questions in the tutorial. Yeah, you can go and try it out. Yeah, make sure you know how to analyze, how to write down the recurrent equation, and how to solve that recurrent equation. Yeah. So next we will find that, okay, so you can see all this is like, I think someone trying to set is a log 2n. Yes. Yeah. So you will find that actually we concern a lot of time is the order of growth. Yeah, here you can see a few algorithm example. For example, yeah, maybe the first algorithm, they take 13n, yeah, this amount of operation. Then the second one is the linear logarithmic. That means it's the n log 2n. The third one is n square. Then the fourth one also n square, but it's the different constant, different coefficients. One is 13, one is 130. The fifth one also quadratic, but plus another 100 constant. Then the last one is exponential, 2 power to n. This is the time complexity of 6 algorithm. So let's set my problem size now n equal to 10. I try different number of n equal to 10, 100, 10 power to 4, 10 power to 6. Yeah. So you can see when you are linear, not surprising, you increase 10 times. Then this one also increase 10 times. Yeah. So linearly increase. If you compare the first one and second one, yeah, you will, okay, not surprising, this one is n log n, so it will be a little bit higher. Then this one is already 10 times higher. Yeah, this one and this one just increase 10 times. Yeah, this one just increase a little bit because it says there's a plus 100. Then this one starting still okay, 0.010, even smaller than this. Yeah, the last one still smaller than this. But soon when you go to 100, yeah, 10,000, 1 million, yeah, you can see that this one increase, you can observe that it's higher than this. Then the rest even worse. When you go to n square, yeah, 10 power to 4, it's already need to take 22 minutes. If let's say one operation, I need to take 1 microsecond. Yeah, then that means when you have a n square number of operation, Yeah, 10 power to 4, n equal to 10 power to 4, take 22 minutes. That's not the worst. It's 1 million, then it take nearly 6 months. Yeah, when you are 120, this one, yeah, after you complete this course, after you graduate, maybe this thing's still running. Yeah, that's not the worst. When you end this one, yeah, also about the same. This one and this one about the same because it's just increase 100 operation only. No big difference. Yeah. So, but if it's a 2 power to n, yeah, probably you have no chance to see the result. Because your PC may be already spoiled. The thing still haven't come out. Yeah, so that is the things you can see that why you need to know. Actually, we're not so concerned about. Yeah, so from this diagram, you learn that actually this constant number, yeah, is not so critical. If your algorithm is already n squared, behind got whatever linear, whatever constant number is not so critical. Yeah, then you can see that when it's linear logarithmic, and then to square. Yeah, the starting is not too big different, but when you go to power to 4, yeah, the difference is quite obvious. That's one thing. Yeah, then between 13 and 130, well, this one take, okay, there are some different, but I would say that it's not that, no, sorry, this one 150. Okay, let me clean the thing first. Yeah, if you look at 13 and 130, these two, yeah, actually the difference not very obvious. When your n getting bigger and bigger, that 10 time difference is no longer critical. It still, there's some impact, but the growth, yeah, this one it increased from millisecond to minutes. This one also grow to hour. Yeah, this one nearly half an hour already. Yeah, then this one go to day. This one also go into day. Yeah, so the growth, normally we concern about the growth, not so much about 10 times or 20 times. Because when you things go from minutes to day, yeah, the things is already very scary. Yeah, there's not much difference between 10 times different or 20 times difference. Yeah, you can see that this one is already go to years. Yeah, so normally, yeah, that's the order of growth. We when we analyze the complexity, the time complexity of an algorithm, we focus on its order of growth. Yeah, and then next is how do we represent them? Yeah, how do we represent them? Yeah. So summarize first. The order of growth, you can see, yeah, if you look at this diagram, you can see that among this order of growth, okay, the most scary one is the n factorial. Starting is not that bad. Yeah, it's still very slow. But once you more than, I think about 7 or 8, you start at, yeah, grow faster than the logarithmic, linear, then quadratic. Then after that, yeah, it will grow much faster than any one of them here. Okay, then the next guy is the exponential. Yeah, you can see just now, n equal to 100, you already go to, you need to run in years. Yeah, if each operation take microsecond to operate. Yeah, even you have a better computer, faster computer, yeah, I think it doesn't help. Yeah, even this thing go to, okay, today most of the PC can run one operation in nanosecond. Yeah, even in nanosecond, it just improved 1,000 times. To this number is nothing. You still won't be able to see the result. Yeah. So that is the problem. So this one will grow exponential. This is also not desired. Then next one, okay, the next two we can compare is the, okay, n square linear is here. Linear grow quite, yeah, if you have 1,000, then you will increase 10 times. You increase 10 times here, this thing will increase 10 times, the operation linearly. Then logarithmic, you will see that you grow is the slowest one among these. Yeah, you grow very slow. You increase 10 times, this one only increase by about 1. Yeah, about 1 times. Yeah, when you increase 10 times your problem size, your input size. Yeah, then after that you compare, this one I already mentioned, you will find that actually you can see these two. Starting there's a difference between this constant, but after a while actually that plus 100 is negligible. Yeah, you can ignore it because it's no different. When you got 1,000, 10,000, 100,000, million, yeah, actually plus 100, you plus 100 additional operation or not, the times you take is no big difference. So normally we can ignore this, the impact in the time complexity. Yeah. Then the next one you compare between 13n square and 130n square. Between these two, yes, always 130n square is grow faster than it's not grow. The two grow is about the same. The growing just like always this one will be take a little bit longer times. Yeah, 10 times, always 10 times higher than the 13n square. But the grow is about the same. The grow you can see they are nearly parallel in this logarithmic diagram. Yeah. So when n go to infinity, actually these two, in terms of, look at their growth is no too big difference. As your n getting bigger and bigger. Yeah. Generally speaking, logarithmic is the one we like to have lah. But unfortunately, not all the algorithm, not all the problem, it can be always be the logarithmic. Yeah, ideally, if we can find a algorithm in logarithmic, of course, it's always better than the linear one. If you can find a linear one, definitely it's better than the n square quadratic, and then quadratic definitely is better than any polynomial n cube n power to 4, 5, 6, 7. Yeah, and then after that the normally we wish that we don't have the algorithm in exponential or n factorial. Yeah, because this thing implied that you cannot let your n too big. Yeah, when your n too big, basically, the computational time will take too long to get the answer, or sometimes nearly impossible to get the answer based on today's technology. Yeah, so okay, then 13n squared 130 have similar goal. Yeah, just this one will be just a little bit faster, 10 times faster. Yeah, but no matter how your n it is, it's just always fixed 10 times faster than the 13n squared. So the question is like, if we can't, a few issue, this is one things, all these constant, you can see that it's not so critical. All these coefficients, the difference maybe not significant. Yes, there is some difference, the computation, but not that significant, not that critical. Compared to is a n square or n cube, that is the second thing. The third thing is like, a lot of times when the algorithm getting more and more complicated, we may not be always able to calculate the exact number of operation. Or sometimes it's too tedious to count every single one. For example, when I declare an integer x, you may see that, maybe I also assign 5. Is it this one considered one operation or two operation? It becomes very subjective, and it's not so important to know it's one or two, as you can see. So when we really analyze the time complexity, we may not really go to count exactly every single one. Operation. We want to know is like, in terms of the problem size, how this is this function, this order of growth, their order of growth. We're not concerned about is 50 or 20 or 30 iteration. We want to know is like, as the n grow bigger and bigger, Yeah, what is the order, the corresponding order of growth of, yeah, order of growth. So the task is convert the algorithm. So log is the big, super big. So the task is to convert an algorithm into a log base. Not always log base. I have to set again. Not all the algorithm is logarithmic. Just now, just give you an example. Yeah, it is a logarithmic, but not always is a logarithmic. Yeah. So, for example, I don't need. So I don't need operation more than 4, for example. Can I choose n factorial? I don't get your question. So sorry. All this is just showing you that if you have an algorithm, the time complexity is n factorial. Implied that this order of growth is grow very fast. This particular algorithm, the computational time is very, very long because it grow very fast. My n just need to increase, my problem size, my input just need to increase a little bit. N factorial will grow very, very fast. But if my algorithm is a logarithmic function, it just implied that it grow very slow. Even my problem, my input from n equal to from 10 to 10,000, I already increased how many? 1,000 times. I increase 1,000 times. Yeah, the computational times is only from here increased to a little bit, maybe 200, about 200, from maybe 30 to 200 only. But compare the same scenario in the linear, yeah, maybe it's already from 100 increased to 100,000. Yeah, you increase 1,000 times, yeah, the computation times will increase 1,000 times. But logarithmic is just logarithmically increase. Yeah, so that's showing you that, yeah, having different time complexity algorithm, the computational times grow very big different. Yeah. And from the diagram, you can see that normally when your n is small, you may not be able to see the difference. Yeah, because n very small, so all of them can calculate very fast. Sometimes n factorial 2 power to n small, they compute even faster than linear or logarithmic. But when your n increase a little bit, yeah, these two grow very fast, but the other maybe grow very slow. Okay. Yeah, so the input size. Yeah, if your input size is small, as I said, if your input size is small, normally no too big issue. But when we analyze the algorithm, we need to consider the when your problem size is arbitrary large number. Yeah, then what happened? Yeah. Is it this is a good algorithm? When we said this is a good algorithm, we should not limit the user only use the small number n. Yeah. So in the order of growth, we need to we consider, we analyze analyze when I have a big number, I have a very big data. Yeah, we need to handle. Yeah, how is the computational times? So when we represent the time complexity, we need to consider when n is large. Yeah. So that is the question. Is like another question. That's another one thing. This thing, another thing we want to consider is like, how do we represent the time complexity? Yeah, what is the critical things we want to tell other people when we have an algorithm? We want to tell people this algorithm is good or bad. Yeah, is it important to show them the exact number of operation we need to run on that particular algorithm? Is it this constant is important? Is it this coefficient is important? Yeah. So we should always choose the smallest growth. We looking for the algorithm with the smallest order of growth. But as I said, that different problem they have. Definitely when you learn about the later you in next module you learn about sorting. Sorting, probably the best sorting algorithm you can find is the n log n. Yeah, in terms of n log n, the order of growth. If you're looking for searching maybe, yeah, you want to search if it's unsorted data, later you will find that you have to check, no choice. If it's the data is not sorted, then you have no other choice that it must be linear. You have to search every component. In the data. So definitely it's a linear. Definitely searching data in unsorted data. Set in the unsorted data set, you definitely have to take linear times to search. You won't be able to find any better algorithm in that way if you not sorted the data. Again, if you not sorted the data. If you sorted the data, then different story. So different problem. We have different way to we need to find out. They have a certain limitation. But of course we're trying to find as good algorithm, as little order, as more order of growth as we can. That's so-called good algorithm. Duplicate for the test was n factorial. 1107 unsorted duplicate for the test was n factorial. I don't get the question. We can ignore the constant when n. Yes, when n is getting bigger, you will find that just now in the example, you can see these two. When n getting bigger, actually this one nearly, actually this green line is the 13n square, but they are overlapping. The difference is too small, negligible, when your n getting bigger and bigger and bigger. So basically this one very obvious, we can ignore. Not only this, even you can try to plot this diagram when you have a 13n square plus n. You will find that actually, we only take the highest order. This one also can ignore because it's negligible. So that's why how do we represent it? Is we need to, so there's someone defined as this asymptotic notation. Big O, big omega, and big theta are the asymptotic notation used to describe the order of growth of a given function. The function is the time complexity here. So the first one is the big O notation. Big O notation represent is the set of function that grow at lower or same rate as g. So if you have any function, your time complexity is lower or same rate as g, we will say that f is in big O g. Then another one is the big omega. So big omega g is the set of function that grow at higher or same rate as g. The last one is the same rate. So set of function that grow at the same rate, we will denote as a big theta g. Okay, so these are three notation. So if you have time complexity, for example, I have my fn is linear. That means fn is equal to n. Then that means this one, if fn is n, then my g, let's say my g is in, maybe this one give a constant. My n is n. Okay, so if these two are two linear function, then basically we can set f is in OGN, no problem. We also can set this one f is in big theta gn, no problem. They are same rate because these two are grow at the same rate. So basically also can be big omega g. But if this thing, my g is the n square, implied that g will grow faster, higher. So that means f is in big omega G. Yeah, because Gn is n square ma. So yeah. Sorry, I said wrongly. Gn is n square. So Fn, okay, sorry. This one should be F is in OGN. OGN. Gn is n square. So Gn grow faster than Fn. Fn grows lower than G. So F is the set of function that grow lower or same rate as G. Yes, so F should be, if Fn is 3n, Gn is n square, F is in OGN. Because if your growth rate is linear, yeah, 3n should be inside the function of n square. Yeah. So if my Gn is n square, so linear definitely grows slower than square function, quadratic function. Okay. So if the other way, then this also implied that you also can set the other way. Gn is in big omega Fn. Okay. Well, just someone invent this notation called asymptotic notation, big O, big omega, big theta. The reason why they introduce this, ideally we want to look for as accurate, as tightest as possible. So ideally we trying to find the time complexity and then represent it in the big theta. That is the ideal situation. But sometimes, as I said, that algorithm can be considered the best case, worst case, and average case. So we may not be able to tell people the exact time complexity of particular algorithm in general. If we not consider, we not mention best case, worst case, and average case. We just want to generally talking about this particular algorithm. Maybe we will use the big O notation. That implied that I'm trying to tell you this algorithm is O n. Yeah, that means this algorithm, yeah, the growth rate cannot be worse than linear. Yeah, because lower or same rate. That means this particular algorithm in any circumsystem, you only can get worse is linear. It can be logarithmic in certain circumsystem. Maybe best case is logarithmic. Yeah. Maybe average case is logarithmic, but the worst case is ON. Yeah. So we may use the O. And sometimes we maybe only know this particular algorithm, the best case scenario. I don't know how worse it can be, but at least this algorithm, no matter how he work, you only can you need to take at least linear times to complete. Then we only can set that this particular algorithm, the time complexity, I only know that the time complexity is in big omega n. Yeah, it cannot be better than this. Yeah. So that is how we use the big O, big omega, and big theta. Yeah. So maybe let us see what is the definition of big O notation. So big O notation is, let's say f and g are two functions. Okay. Then fn, we set fn is said to be in OGN, denote as fn in OGN. That means fn is bounded above by some constant multiple of gn for all large n. Yeah, the set of function can be defined as this. Okay, this is the definition. So in the diagram, what does it mean? They say as long as you're able to find a number n naught, yeah, after this number, after this, your problem size, your input size, after this, yeah, your fn is bounded, yeah, is bounded above by some constant cgn. That means cgn is always above of fn. It's always bounded. Yeah, fn is always bounded. It's bounded. Okay, so that means gn bounded Fn, okay? Yeah, so Cgn is the ceiling. Is a ceiling. Your Fn cannot be more than that. Then you can set that Fn is in all Gn. Example? Yeah, just I already show you actually. Fn is 4n plus 3. Gn is n. Yeah, so I can easily find that C equal to 5, n not equal to 3. Yeah, in this circumsystem, you find that, yeah, it fulfill 4n plus 3 definitely less than or equal to 5n for any n greater or equal to 3. Right, as long as this statement is true, you can fulfill this statement. Yeah, you can find a C, you can find a n not, fulfill this statement. Yeah, then you can conclude that Fn is in all Gn. Yeah. So that's mean your this algorithm cannot worse than this particular Gn function. Yeah. Cannot grow faster than that. It's definitely lower. Yeah, that's recall just now the earlier. Yeah, it definitely lower or same rate. It can be same rate. Yeah, this example actually they are grow in the same rate. This is a linear function. This is also another linear function. They are in the same rate. So you can set that this is Fn is all Gn. Okay, in compute, okay, another notation you need to take notes here. In computer science, normally they write equal. Yeah, by right, in mathematics, you should write it's a set of function. All n is a set of function. So you're supposed to set it. This function is in all Gn or all n. Yeah, but in computer science, yeah, normally they, for simplicity, they just use equal. Mathematically speaking, not very correct, but it's a convention people use right in this way. Because later you will find that when you want to simplify, yeah, they may do some mathematics operation, yeah, simplify the expression, yeah. So for convenience, they use the equal signs. Yes. So this thing, I just briefly introduce you all this thing. Later, you also need to use your discrete mathematics. So that's why the CZ2101, the prerequisites is 1107 and the discrete mathematics. Because after you know what is the big O, big omega, big theta, and you know how to write, how to use this thing to do some simple analysis, next level, they will combine the discrete mathematics and this part together to analyze all the algorithm. Yeah, those more advanced algorithm. Yeah, so that's why I keep saying this thing, you need to do some mainly is do some preparation for the next level. Yeah, in this level, mainly is still 80% is the implementation, 20% is the quiz. Well, you maybe don't feel 20% is important. Yeah, but next level, you really need all these things. Yeah, so don't just learn based on the mark in the CA. Yeah. So, okay, so this is the big O notation. Well, this is one way to find out what is the big, whether this function is in OGN or not. Sometimes when you, yeah. Okay, same thing. When you n go to n square or n cube, not surprising that you can easily find a Cn and n naught to fulfill this criteria. So again, yeah, Fn is in OGN. Yeah. So you can set if Fn is equal to OGN, we said that Gn is asymptotic upper bound of n. Then the big O notation, another way to find whether this thing is in OGN, you'll need to use your the L'Hopital rule to find the limit, yeah, of Fn over Gn. If this thing less than infinity, implied that less than infinity, that means implied that your Fn will grow slower than the Gn or equal. If they have a growth rate is about the same, this thing will give you some constant. The limit will give you some constant. If Gn grow faster, it will give you 0. right? So that means this thing implied, what does it imply in mathematics? The meaning is like Fn won't grow faster than Gn. Yeah. So you can use this to find out that if you find this thing is a constant, yeah, because these two are linear. So not surprising, the limit will give you a constant number. So less than infinity implied that Fn is in OGn. This thing, not surprising, will equal to 0 because n cube grow faster. So this thing, when you take the limit, not surprising that it will equal to 0 because the denominator grow faster. Yeah, so it will less than infinity. Again, you can conclude that Fn equal to OGn. Yeah. So a constant C. Yes, if it's a algorithm is a constant C, then it's O1. You can simply say it's O1. Yeah. O1 is equal to O2, O3, O4, O5. They are the same thing. Okay. So this is the big one of the very important notation to represent the time complexity. Big O notation. Yeah. So another one similar is just the other way. Yeah, it's bounded below. Fn is bounded. If Fn is bounded below by some constant multiplied by Gn, then we said that this is Fn is in big omega Gn. Yeah, that means that the CGN provide the lower bound for Fn. Yeah, that means your Fn after certain number, some big n naught. Yeah, anything bigger than n naught. Yeah, Fn is always grow faster, higher, bigger than CGN. Yeah, so yeah, just reverse another way. You will find that if Fn in big omega Gn, we said that Gn is asymptotic lower bound of Fn. Yeah, so it's asymptotic lower bound of Fn. The key word. It's not really lower bound. It's asymptotic lower bound. Okay. Another one, the big theta. Okay, before I end today's lecture. Yeah, big theta is the tighter bounds. The thing is mounted both above and below. So you have a two. You can able to find C1 and C2, some constant C1, some constant C2, and then and N0 such that it fulfill this criteria. Then saying Fn is fall between two, yeah, Gn, C1G and C2G, then your F will be in between. Yeah, generally speaking, yeah, implied that Fn and Gn are grow at the same rate. Otherwise, it's not possible you can find a constant, yeah, two constant, which one give you the upper bound, asymptotic upper bound and asymptotic lower bound. Yeah. So this thing, same thing. If I mentioned just now, yeah, big omega, you also can use taking the limit. Yeah, to find if the limit greater than 0, then it's big omega. If greater than 0, Fn is in big omega Gn. Then if it's give you a constant, implied that Fn is in big theta Gn. Okay. So if Fn is big theta Gn, then we said that Gn is asymptotic tight bound of Fn. Yeah, Gn is asymptotic tight bound of Fn. Okay, summarize. Yeah, if you trying to find taking the limit, using the limit, I think yeah, you will find the limit is one quite easy to determine. Limit, if I take should I have the limit? Yeah, Fn, when n grow to infinity, my Fn over Gn, if this limit give me 0, yeah, I can set that Fn is in OGN. If that's mean implied that Gn grow faster. Yeah. If they give me a constant, well, constant, that means is the big theta Gn. If it is a big theta Gn, that means this thing is also can set Fn is in big omega Gn. Fn is in big O Gn. Yeah. If this thing go to infinity, Fn over Gn, n go to infinity, then this ratio also go to infinity. That means Fn grow faster. Fn grow faster imply that Fn is in big omega Gn. Yeah. So that is how we can use asymptotic notation to represent that your time complexity belong to which category. To give, of course, title bound is very clear. Once you determine this is a linear function, then big theta n, that means this thing is in linear function. Then normally big O and big omega, big O is trying to give you an idea. It's like this thing won't get worse than this particular function, O(n). If you said that this algorithm is O(n), that means your algorithm cannot worse than that. Growth cannot be faster than n. If you said that the algorithm is in big omega n, implied that this algorithm cannot be you only know the best case, the best scenario you can achieve is n. At least you need to take linear to run this particular algorithm. Yeah, the growth is linearly, at least. Yeah, it can be worse than that. Yeah, but your knowledge, you're only able to know that it's a big omega n, the best case. Yeah, you only know it's best case. Yeah, maybe you don't know the worst case, so you only can comment that it's a big omega. Ideally, you should know everything. If you understand the whole algorithm well, you can analyze. Yeah, this is what normally the case in this module so far. Later, you find that not always you're able to determine the thing in big theta. You only know it's best case or worst case sometimes. Yeah. So you will represent, if you know everything, all the scenario, you can judge, then you probably can write it in the saying that this algorithm is in big theta n or big theta log n and so on and so forth. Okay. Before you go for the test, okay, I close today's lecture by this question. Yeah, so given these two functions, can you tell me whether f is in OGN, whether f is in big theta g, and whether f is in big omega g of the following two functions? Fn is log 2n cubed, Gn is log 2n. Both, all of them. Both? You got three things. Yep. I hope you know that this thing actually can rewrite it in this. So based on, I can use a few ways. First, I use the conventional definition. Then not surprising that Fn is less than or equal to 3 equal to 3 Gn. Basically, it's equal to 3 Gn. Yeah, so definitely I can find some constant. I can easily to find my constant. I can find the constant C1 and C2. I can let C1 equal to 5, C2 equal to 2. Yeah, definitely it's title bound. So definitely they are title bound. So definitely it's OGN, big omega Gn, and big theta Gn. Generally speaking, yes. Overall, you can find that Fn still grow a little bit faster than Gn in this. But when we're talking about all big theta and big omega, we are considered the order. So the order, based on the definition, you can see that actually we're not concerned about that little faster. Yeah, that constant, this coefficient is not so critical. That is not something we concern when we represent the algorithm in all asymptotic notation, big O, big theta, and big omega. Another way you can try to take the limit is showing you that Fn over Gn is just a constant tree. That means this Fn and Gn, they are grow at the same rate. Yeah, overall, if you really run the program, Fn will be a little bit faster than Gn, a little bit faster. But the order of growth, the keyword is order of growth, they are the same. Yeah, if you really if today you really have two algorithms, one of them is the time complexity is Fn, the other one is Gn. Yes, Fn will be, you will find that Fn will, that particular algorithm will run a little bit slower, it will take longer times because it grow faster, the time complexity grow a little bit faster. Yeah, it will take longer time to finish the program. Right, okay. But the overall we consider is order of growth. Both of them are logarithmic function. Yeah, whether it's 3 times slower or how, that is not what we concern. Overall, both of them are, their order of growth are logarithmic function. So they are in the same category. They are fall into the same order of growth. Yeah, so we can set that Fn is in all Gn and big omega Gn and big theta Gn. That is what the asymptotic notation meanings. Yeah. We look at, we only concern the trend. We only concern the trend. We only concern about the order of growth. We're not concerned actually which one run a little bit faster or which one run a little bit slower. That's one thing you need to know. Second thing you need to know is that when you set F grow faster than G, actually F, if your time complexity is Fn, actually that particular algorithm actually need to take longer times to run. Yeah, because order growth is grow faster. The algorithm will take longer times to run, to finish. Okay? So these are the things you may need to think about it. Okay? That is the today lecture. Maybe Wednesday I will finish the rest about the simplicity or this. Yeah, and I will introduce another one is the algebra expression. Yeah. One of the application of stack and cube in Wednesday lecture. Okay, thank you. Any question? If not, I will end today's lecture. Okay, good luck in your test. Bye. Can you re-expand the first part? Re-expand the first part. Your first part, you mean first part? Do they only cover the asymptotic notation? Order of growth? Oh, okay. In the beginning, we're talking about this question. Yeah. So, your question is, okay, the question in this question, okay, first, the question just asks you, they not really ask you the whole algorithm, the time complexity of the whole algorithm. They only ask you what is the number of multiplication. Okay, so you just need to know the number of multiplication. That's first thing. Okay. The second thing is the assumption is n equal to 2 power to k. So for sure that n is even number. When n is even number, n definitely is an even number. And in each function call, I guess you should be, where the 2? Yeah, so what is the number of multiplication? So it's even number. So if it is even number for sure, then you only have 2 multiplication here. One is here. The second one is here. So only 2 multiplication. Each time I only have 2 multiplication. Yeah. In each call, each recursive call have 2 multiplication. Then I will do the function call here. I will do the recursive call here. So, and then reduce the n by half. Reduce the n by half. So this is the recurrent equation. Okay. Once you have this, the second thing you need to know what is the base case. The base case is here. When not surprising that you can see every recursive function you n divide by 2, divide by 2, divide by 2. So your W0, when n equal to 1, W1 will be equal to 0. No multiplication. Yeah, this line, no multiplication. You already return x. You just simply return x. So there's no multiplication in the base case. Once you have these two, basically you can solve the problem. Yeah, once you have this one, every recursive call, you divide by 2. And then each time you will run 2 multiplication and then reduce the problem size by half, then recursive call. Yeah, so next one will be 2 plus 2. In this recursive call, you will run another 2 multiplication plus t over n divided by 2 power to 3. Because the n is 2 power to k, so implied that your n is always even number. Yeah, simple example. If you start from 256, divide by 2 is 128, even number. Divide by 2, 64, still even number. Divide by 2, 32, still even number. Yeah. So, but then why would we return half power times half power? Shouldn't it be returned 2 plus half power? No, the question is asking the number of multiplication. So you only did 2 multiplication. Yeah. So actually you don't need to concern about what actually this algorithm trying to do. Okay? That is not the question asking. Yeah. The question is just asking you the number of multiplication. Okay? Okay, then I answer sorry question. Okay, sorry T. You think about it, huh? Then sorry T is asking about the asymptotic notation. Let us go to asymptotic notation. So I'm confused about the meaning. So asymptotic. Oh, so whatever the algorithm does, we are not. Yes, when that question is just ask you about the number of multiplication operation only. So what exactly they doing the calculation is not the topic we are discussed at here. That is not what. Yeah, don't. Sometimes those questions, I just want to test you the number of multiplication. What exactly they calculate is not the thing I'm concerned so much. You know, yeah. You can think that is the time complexity problem, not the algorithm itself. Okay. So sorry, asking about the asymptotic notation. So big O, big omega, big theta is I'm thinking what you meaning about the meaning confused about the meaning of asymptotic. So is the you can see that when we talking about in the early example, we concerned about what actually when we calculate all these algorithm, including just now that example, the number of multiplication, actually we want to really count every single operation. It's not very practical and also not very important. We really want to know is this particular algorithm, the order of growth. As long as it is a logarithmic, yeah, we know that you will grow very slow. If it's a linear one, you will go a little bit faster than logarithmic. When it's the linear logarithmic n log 2n, you will go faster than linear, but slower than the n square. Yeah, so when you will find that actually when we analyze the time complexity, we concern about the trend. The trend, the order of growth. So people come out this asymptotic notation is trying to figure out the trend. Yeah, whether this particular time complexity, this f, the time complexity f is grow at lower or same rate as g. G can be normally is a general function like n square, n cube, log n, and so on and so forth. Yeah, linear, logarithmic, quadratic, or exponential. Yeah, so your time complexity you come out is a 3n plus 20 or n square plus n or n square plus log n. Yeah, is it this particular function, the order of growth is at lower or same rate as g or not? Then we represent this particular f is in OGN. If it fulfill is a grow at lower or same rate as g, then we said f is in OG. Yeah, so that is the asymptotic notation means. Asymptotic, that means the trend, the n growing, as your n increase, how this function, the growth, the relationship between g and f. Okay, so it's a set of function. That's why it said set of function. That means OGN is a one family. So maybe if your g, let's say your g is in my gn is n. That means n definitely is in the OGN. 2n also is there. 3n plus 2 also here. Anything is lower than that, lower one can be log n. Lower one can be log 3n. Lower one can be constant 3. Higher one can be n cube, 2 power to n, 3 power to n, n square plus 4, whatever you name it, greater than linear. Yeah, so basically if my gn is n, then those logarithmic definitely is lower, constant also lower. Yeah, if it's all the polynomial n cube, n power to 4, 5, 6, 7, 8, 9, 10, whatever you name it, exponential function, all this definitely is higher rate as g. Higher than g I would say higher than g. Yeah. So these are set of function. So whether your f is fall into which category, That is what we concern about when we represent the coin complexity in this asymptotic notation. Because in practice, like I said, we're not so concerned which one run a little bit faster than the other one. We concern is like, as my n increase, what is the trend? Is it this growth rate is about same as this category of function or that category of function? Yeah. So it is about the growth rate. Yeah. That's why in the earlier we talk. Why I need to give you the example is that order of growth. Yeah, because all this asymptotic is order of growth. Yes. Yeah. So that is the things about the asymptotic notation. Trying to say, yeah, it's always people have this confusion. Good, thanks. Okay, if no further question, see you in Wednesday, 4:30 to 5:30. Goodbye. If you have any question, you still can email me. Okay.